Hello students, welcome to the 52nd lecture on particle physics. And today we are going to talk about how to write wave function for the baryons and mesons to get the charge of the baryons and mesons or to get the magnetic moment of the particles, and then we shall talk about how to calculate the mass of the baryons and mesons using quarks. And to start with, as we know that hadrons are bound states of quarks and antiquarks, baryons are made up of three quarks and mesons are made up of quark anti-quark pair. Therefore, the simplest example of a multiplet of a SU2 is the fundamental representation of two dimension, which is an object that can occur in two states that we have discussed. For example, proton and neutron belong to a SU2 representation, and in this representation, if you recall, we said that they are members of nucleon doublet, and in the doublet we have the proton with isospin half whose projection is plus half, and neutron whose isospin is half and projection is minus half. Okay, and we call it as nucleon state. We also represented it by half plus half, and this is proton, and neutron is represented by half minus half. Now SU2 stands for a special unitary group in two dimension, which has got three generators. As we know that for SUN the number of generators are n square minus 1. Since this is SU2, therefore you are talking about any two objects. Here it can be a U quark and a D quark. Therefore, whether we are talking about proton, neutron, or U and D quark, or spin up and spin down in the case of spin half particles, the number of generators here, this will be 3. If you recall, in the case of spins, we had the generators as the Pauli spin matrices, which were Hermitian, traceless, and this was the property of sigma 1 0 I minus I 0 1 0 0 minus 1 for the sigma 3. Therefore, these are the generators. Then even we talked about the Casimir operators, which was sigma square is sigma 1 square plus sigma 2 square plus sigma 3 square. And in the case of SU2, we have only one Casimir operator, and this Casimir operator, whether I represent it by say J square, they commute with, say, this is I am calling in general as J1, J2 as well as J3. Therefore, J square commutes with all these three operators that we are talking about, sigma 1, sigma 2, sigma 3, whatever you like. Now, similar to this sigma 1, sigma 2, sigma 3, we also introduced isotopic spin operators, like instead of sigma 1, we call them as tau 1. Here we call this as tau 2 and tau 3. Then if you recall, we introduced isospin raising operator and isospin lowering operator and all that. Now this is the general scenario when we talk about proton, neutron as isodoublet, up quark and down quark as isodoublet. Therefore, today we are going to talk about SU2 representation, where we have two objects, U and D quark, and mind it, this U and D quark are represented by half plus half for a U quark and half minus half for a D quark. Therefore, a U quark state and a D quark state that we are talking about, and we are talking about the SU2 representation. And then if we extend from SU2 to SU3, this can be done by including a strange quark, then to SU4 by including a charm quark, and up to SU6 by including the top quark. Therefore, here first we are sticking to SU2, U and D quarks, and then SU3 for U, D and S quarks, etc. Now what we have discussed, if you can recall, that if we have two isospin half objects, I'm not telling you which one of them. They can be both U, they can be both D, one can be U and another can be D. Both are isotopic spin half objects. Let us write it by I1 is equal to half and I2 is equal to half. Then this will be also true for proton and neutron. But we are considering here the two quarks, and these two quarks are non-strange quarks, and these are U and D quarks. Now the total isotopic spin, this will go from I1 minus I2 to I1 plus I2, and this will give us 1 and 0. I1 plus I2 will give us 1 and I1 minus I2 will give us 0. Now this 1 will have a projections plus 1, 0, minus 1, and this 0 will have projection, let me just call it by IZ, the Z component or the third component. Okay, now IZ is plus 1, 0 and minus 1 for 1 and 0 for 0. Therefore, the different states that we are talking about, they are 1 plus 1, 1 0, 1 minus 1 and 0 0. These are the four possible isotopic spin states. They can be also four spin states if they are representing the spin of the particles. Now, if we want to get a total isotopic spin half, 1, and whose projection should be plus 1 from the two isotopic spin half objects, we can get, since projections are only algebraically added, therefore that means this is fixed to get plus 1. Then the only possibility that we have, two half objects to give us 1, because 1 can only have projection plus 1, though it can be 0 also, but 0 cannot have a plus 1 projection. Therefore, it has to be 1. Okay, and then these we are forming from half plus half, I1 IZ1 and I2 IZ2 half plus half. And half plus, you see, this is a Clebsch-Gordon coefficient about which we have discussed, and we have seen that for maximum projection on either side, Clebsch-Gordon coefficient is 1. In general, I told you that Clebsch-Gordon coefficient matrix is represented by J1 M1, J2 M2 its projection, J whose total projection is M. Now we also write it as J1 M1, J2 M2, and whose projection is Jm. These are real numbers and they have been tabulated. If you just Google Clebsch-Gordon coefficient, you can see these evaluated numbers without going to the details of evaluating it, that if we have half plus half, half plus half and 1 plus 1, then Clebsch-Gordon is 1, and if Clebsch-Gordon is 1, then we are left with half plus half and half plus half, and that means this is 1. This is representing a U state. Therefore, in the first state, you have a U quark. In the second state also, you have a U quark. Therefore, if you want to get 1 plus 1 state, the option is only in both these states you have U quarks. Like if we have two spin half particles, then if we want to have 1 plus 1, then if you can remember from your quantum mechanics classes that this is only possible when both of the spins of these particles are in the upward direction. Therefore, or if I talk about, which we have discussed in the class, protons and neutrons as isodoublet, then this is possible only when in both these states you have two protons. Therefore, whether I talk about in both these states two protons or in both these states two up spin particles, no matter whether I am talking about two electrons or two protons or two neutrons, but if I want to get a state 1 plus 1, then the only possibility is that both of them are in the upward direction. Here also, when I want to get an isotopic spin state by combining two isotopic spin half particles, then the possibility is, and that is the only possibility, that in both these states you have U quark. Now similarly, the other point is, instead of 1 plus 1 state, if I want to form 1 0 state, now in the case of 1 0 state, you have, say, this is one state, this is second state. What I wish to get 1 0, that means this is 1 whose projection is 0. Now 1 we can get by half and half isotopic spin projection, then will be, to get 0 will be plus half for this and minus half for this, because projections are algebraically added, and we have for the first state half plus half, and for the second state half minus half, and then what we have, then plus, now the possibility that in the first state we have the projection minus half, and in the second state we have the projection plus half, then we have half minus half, and then half plus half. Now this is J1, J2, capital J, M1, M2, capital M. Now if you look at the Clebsch-Gordon table, this will be 1 by root 2. This is a U quark and this is a D quark. This is also plus 1 by root 2. Then if we have plus 1 by root 2 plus 1 by root 2 in both the cases, then we can take 1 by root 2 common, and we may write it as U quark in state 1, D quark in state 2 plus D quark in state 1 and U quark in state 2. See here, this is half minus half. Then if we want to write for 1 minus 1, again you see, we are talking about 1 minus 1. Minus 1 we can only get when minus half and minus half will be algebraically added, and that means both of the projections should be minus half. Then in that case, what we are going to do, we are going to write it as half minus half minus half, 1 minus 1. We are forming J1 M1, and the other one is also half minus half. Therefore, this is giving us, this is again the maximum projection on the other side. This value is 1. Therefore, this is a down quark in state 1 as well as down quark in state 2. Now we have the fourth case where we have 0 0. Now this 0 0, as we have seen that half minus half will give us 0. Therefore, everything is fine. This we are talking about 0. But this, when we are talking about 0 can have only a projection 0. This can be possible when this is plus half, this is minus half, And also the other case where in state 1 you have half minus half particle, and in the state 2 you have a particle whose isotopic spin is half and whose projection is plus half. This is how we write them. Okay. Therefore, this Clebsch-Gordon, as we have discussed it in one of the classes, is 1 by root 2, and this Clebsch-Gordon is minus 1 by root 2. See here, what I am telling you, that this is plus 1 by root 2 and this is minus 1 by root 2. These Clebsch-Gordon coefficients are the real numbers, but they contain either positive sign or negative sign, and this is plus 1 by root 2 for the first case, Clebsch-Gordon coefficient, and for the second Clebsch-Gordon coefficient, this is minus half. Therefore, we can write it as 1 by root 2 u1 d2, 1 by root 2 u1 d2, and then minus sign. This is arising because of the fact that for the second part the Clebsch-Gordon is minus 1 by root 2 minus d1 u2. Therefore, what you are noticing, that for the four states we have, what we have the possibilities as, and the only possibilities. We have the possibilities as for 1 plus 1, a U quark in state 1 as well as a D quark in state 2, a U quark in state 2, for 1 0, 1 by root 2, U quark in state 1, D quark in state 2, plus D quark in state 1 and U quark in state 2. For 1 minus 1, in both these states you have D quark, and then for the fourth case 0 0, for the fourth case 0 0, you have 1 by root 2 u1 d2 minus d1 u2. Therefore, the important point is that if I am from two objects, I want to get an isotopic spin state 1 where there are three possible projections, and then for isotopic spin state 0 there is only one projection. We have these possibilities. Now, if you recall, when we were discussing about protons and neutrons, then in both these states you had proton here, you had P1, P2, you had here in state 1 proton, in state 2 neutron, and then in state 1 neutron and proton, and so on. And here you had with a negative sign. Now, these three states are symmetric states, because if you interchange particle 1 with a particle state 2, which is in state 2, there is no change of sign. Therefore, these three states are symmetric state, while if you interchange here U by D, you are picking up a negative sign. Therefore, this state is anti-symmetric state. This state is anti-symmetric state. Therefore, you have three symmetric states with one, because there are three possible projections, and one anti-symmetric state. Now, what happens if we talk about strange quark also? Then the fundamental representation for UDS flavors of quarks is SU3, and the fundamental representation of spin for such particles, as you know, that whether it is U quark or D quark or strange quark, all of them are spin half particles, and if they are spin half particles, then there are only two possibilities of projections. One is plus half and another is minus half. Therefore, if you are talking about two states where you have got two fermions, they can be two u quarks, they can be u and d, or d and u, or both of them d, or two electrons, two positrons, two protons, whatever you talk about. If you have two spin half objects, then we know that the possible projections can be only plus half and minus half, and then you have the similar to what we had for the isotopic spin states, we will have the spin states. Therefore, in the case of spin, whether you are talking about SU2 or SU3 or SU4, there is only possibility of getting SU2 from for the spins, and therefore if we are talking about three flavors of quarks and the spin representation of the particles, then in total you have a 6-dimensional representation of SU6, where you have U in the up state, or U can be down state, D in up state or D in the down state, or S quark in the up state or S quark in the down state. Now, physically in the quark model, the intrinsic SU3 degrees of freedom will be multiplied by the SU2 spin of the quarks. Now, the SU6 wave function has to be totally symmetric if we are talking about mesons, as mesons are described by Bose-Einstein statistics. The wave function has to be symmetric. While if we are talking about baryons, then baryons are described by antisymmetric wave functions. And if we are talking about antisymmetric wave functions, then we have to be careful. When we are talking about the total wave function of the baryons, then we have to keep in mind that the baryon wave functions will depend upon how these three quarks are localized in space, and that means the wave function that is describing the position of the quarks, and we know that the position of the quarks hardly matter whether if I am writing three quarks and a three-dimensional space, whether this fellow is at R1 or this is R2 or this is R3, that is immaterial, and that means this wave function has to be symmetric. Now, if you recall, we had introduced on the last turn color to an intrinsic quantum number to the quarks, and this was to first save the Pauli's exclusion principle, and then experimentally it was also found that to explain some of the results, we need the case where quarks follow or having an internal degrees of freedom, and that we call by the name red, blue and green, that the quarks come in three colors, and this color wave function is always antisymmetric in nature. This is always antisymmetric in nature. While baryons have to be, this total wave function have to be antisymmetric. Therefore, the total wave function has to be antisymmetric to define fermions, whether I am talking about baryons or even I am talking about the leptons. The total wave function should be antisymmetric. Now, the total wave function consists of the wave function that describes the position of the quarks, the wave function that contains the flavor of the quarks that give rise to a certain baryons, and that is why I am writing it as psi, which is function of isotopic spin. And mind it, I am putting a bold psi. This is simply to convince you that this isotopic spin is not a vector in Euclidean space. This is a vector in isotopic spin space, which is a hypothetical charge space. Therefore, we should never get confused with the vector in ordinary space, and therefore this is I, and then we have a wave function depends upon the spin of these quarks. Therefore, we have an spin and again an intrinsic property of the particle, and it is entirely an independent entity. Then we have color. Therefore, if this is by choice always antisymmetric, therefore these three guys have to be symmetric in nature to have this antisymmetry. Therefore, this has to be antisymmetric by the definition of Fermi-Dirac statistics. This guy is the localization of quarks. This is symmetric. This guy is antisymmetric. Therefore, these two together should be antisymmetric. Therefore, localization, the wave function which is describing the localization of the quarks, that is symmetric. The color wave function is antisymmetric. Since the total wave function has to be antisymmetric, therefore they together, psi isotopic spin and psi spin, they together they have to be symmetric. Therefore these two have to be symmetric. This is antisymmetric, this is by construction symmetric, and then only, that means this symmetric part we can get from symmetric and symmetric component, or antisymmetric and antisymmetric component. That means minus 2 times minus 2 is also 4, and 2 times 2 is also 4. Therefore, symmetric times symmetric will give you symmetric, and antisymmetric times antisymmetric will also give you symmetric. Therefore, this is the point that psi r is symmetric, psi color is antisymmetric. Therefore, psi I times psi s, that has to be symmetric. And this is how we construct the baryon wave function, because in quantum mechanics all the observables that we talk about is obtained using the wave function of a system. Okay, you obtain the expectation value, and observable corresponding to the operator that you are talking about is basically the number that matches with the experimental observable, whether this is charge operator, whether it is a magnetic moment operator, or whether whatever you talk about. That means if I want to get the charge of the baryon, charge of the proton, charge of the neutron, charge of the delta, charge of the meson, whatever you talk about, you have to obtain the expectation value corresponding to the charge operator. And the wave function has to be normalized, because in quantum mechanics we accept only a normalized wave function. Therefore, the important point is that your wave function has to be normalized, and you have to obtain the expectation value corresponding to the given operator, and the eigenvalue that you will get will be the number that should agree with the experimental number if you are having a correct wave function to describe the system. Therefore, in quantum mechanics, the most important point is to get first a well-defined wave function to describe the system. This is what we are going to build to obtain the charge of the protons or mesons, or the magnetic moment of the baryons and the mesons, etc. Therefore, to us, the important point is that we have to obtain the total wave function psi b. And what I am telling you, that why we need this total wave function, this is because in quantum mechanics any observable is defined as the expectation value of the operator, and the denominator is to take care of the normalization. Therefore, here I should write BB. This should be 1. Our wave function should be properly normalized. And then here, when we are talking about the charge of the particle, charge of say proton, then this will be the charge operator which will operate on the different quark states. If you believe in the quark model, and if you are sure that all the baryons and mesons are made up of 3 quarks in the case of baryons, and quark anti-quark pair in the case of mesons. Therefore, psi r in principle is symmetric, as this hardly matters which quark is placed at the three positions. Psi color is completely antisymmetric by constitution, which leaves us the only possibility of psi I, psi s being symmetric. This is what I have discussed. We shall see that the full set of SU3 wave function will consist of psi symmetric wave function, psi mixed symmetric wave function, and psi mixed antisymmetric wave function, and the four combination as psi antisymmetric. I will discuss later what is meant by psi mixed symmetric wave function and psi mixed antisymmetric wave function, and SU2 will consist of psi s, psi ms, and psi ma wave function. Those states labeled S are totally symmetric. Those states which we label by A are totally antisymmetric, while ms stands for mixed symmetric wave functions and ma stands for mixed anti-symmetric wave function. And then, to make life simple, what I am doing, instead of writing a bold I, we are just writing it by I. So therefore, don't get confused with this by looking at this I, because always we will talk about the projections of I. Therefore, instead of this bold I, we are using simple I. Now, what we have discussed today, that U quark has the isospin projection as half plus half, and D quark has isospin projection as half minus half, and the total isotopic spin is going from I1 minus I2 to I1 plus I2, such that you are getting states like 1 and 0, and then possible projections we have discussed in the class. For I equal to 1, it is plus 1, 0, minus 1, and for 0, it is always equal to 0. Now we have formed 1 plus 1 state, and when we form 1 plus 1 state, we saw that it is only U1, U particle in state 1 is U, particle in state 2 is U. Then for 1, 0, we found that this is 1 by root 2, particle in state 1 is U, particle in state 2 is D, and plus particle in state 1 is D, and in second state it is U. Then 1 minus 1 we obtained. In both the cases, we have down quark in state 1 as well as in the state 2. Then we had isotopic spin 0, whose total projection was 0. This was possible as 1 by root 2 U1 D2 minus D1 U2. Therefore, to summarize, if we are considering two objects, U and D quarks in SU2, then we have these possible combinations. These combinations we have discussed, and we have found that 3 of them are symmetric and 1 of them is completely antisymmetric. Now, we shall talk about system of 3 objects in SU2 representation, because we know that baryons are made up of 3 quarks, and if we talk about proton, neutron, delta plus, delta 0, delta minus, delta plus plus, these are all made up of 3 quarks, but all 3 of them are either U or D. Like proton is made up of UUD quark, delta plus plus is made up of 3 U quarks, etc. Therefore, the important point is, in the next class, we are going to talk about 3 objects. All 3 objects will be either U or D. That means we have 3 states, because all the baryons are made up of 3 quarks. Therefore, we must have 3 states to put these 3 particles. Then what we will talk about? We will talk about the fact that in these 3 states, we are going to put, say for example, 2U 1D or 2D 1U, or all of them as U or all of them as D's, etc. And then we will see that how to construct flavor wave function. That means we will construct psi for isotopic spin space for the baryons, and then we can similarly obtained the wave functions for the mesons. Let's stop here. Thank you very much.